Look around you. The earth beneath your feet is spinning, completing a full rotation every 24 hours, carrying you through space at over 1,000 kilometers per hour at the equator. This rotation is so constant, so smooth, that you cannot feel it directly. But if you could step outside your normal frame of reference, you would see the ground moving beneath you, the horizon rotating, the entire planet turning like a giant sphere in space. The moon orbits the Earth, itself rotating, though locked in synchronous rotation, so we always see the same face. This tidal locking is a result of billions of years of gravitational interaction, a dance between two celestial bodies that has reached a stable equilibrium. The moon's rotation and orbit are now perfectly synchronized, a pattern that will persist for billions of years to come. The Earth orbits the Sun, which itself rotates, completing a turn every 25 days at its equator. The Sun's rotation is not uniform. Different latitudes rotate at different rates, a phenomenon called differential rotation that creates the complex magnetic field patterns we observe. This rotation drives the solar dynamo, generating the magnetic fields that create sunspots, solar flares, and the solar wind that streams outward through the solar system. The Sun orbits the center of the Milky Way galaxy, which spins like a cosmic whirlpool, taking over 200 million years to complete a single rotation. This galactic rotation is not like a rigid wheel, but more like a fluid, with different parts moving at different speeds. The spiral arms trace out the rotation pattern, creating the beautiful structure we see in images of other spiral galaxies. And on the smallest scales, electrons spin around atomic nuclei, while the particles themselves possess an intrinsic quantum spin, a fundamental property that cannot be stopped or changed. This quantum spin is not rotation in the classical sense. Electrons are point particles with no size to rotate, but it behaves like angular momentum, creating magnetic moments and determining how particles interact. The quantum spin of electrons is what makes atoms stable, what creates the structure of matter, what underlies the chemistry of life itself. Everything turns. From the smallest subatomic particles to the largest cosmic structures, rotation is everywhere. It is not an accident or a coincidence, but a fundamental aspect of how the universe works. The question is not whether things rotate, but why. Why does everything turn? What is this repeating rhythm that permeates existence at every scale? This is not merely a question about mechanics or physics, though it is that. It is an invitation to contemplate something so fundamental to the universe's structure that without it, reality as we know it would be impossible. Rotation is not just motion. It is a principle, a pattern, a rhythm that echoes through space and time. It shapes planets and stars, creates day and night, drives weather patterns, and underlies the very structure of matter itself. As you prepare to rest, consider this: you are spinning. Right now, as you read these words, you are being carried around by the Earth's rotation. The bed you will lie in, the room around you, everything is turning. This motion is so constant, so smooth, that you cannot feel it directly. But it is there, always, a gentle rotation that has continued for billions of years and will continue for billions more. The universe's repeating rhythm is not just about physical rotation, but about cycles of all kinds. Day follows night, creating a fundamental rhythm that structures life on Earth. This cycle is so constant, so reliable, that it has been used as the basis for timekeeping for all of human history. The rotation of the Earth creates this cycle, but the cycle itself has become something more, a pattern that structures consciousness, that creates the alternation of activity and rest, that shapes the very experience of time. Seasons follow seasons, creating yearly rhythms that drive migration, hibernation, breeding, and the growth cycles of plants. The seasonal cycle is created by Earth's orbit around the Sun combined with the tilt of Earth's rotation axis. As the Earth orbits, different hemispheres receive more or less direct sunlight, creating the seasonal variations. But this cycle has also become something more, a pattern that structures agriculture, that creates cultural celebrations, that marks the passage of time in human experience. Life follows death in cycles that repeat across generations. Organisms are born, grow, reproduce, and die, but their offspring continue the cycle. Species evolve, adapt, and sometimes go extinct, but new species arise to take their place. This cycle of life and death is not just biological, but cosmic. Stars are born and die, galaxies form and evolve, the universe itself may have cycles of expansion and contraction. Stars are born and die in cycles that have been repeating for billions of years. Massive stars live fast and die young, exploding as supernova and enriching the interstellar medium with heavy elements. These elements become part of new stars and planets, creating a cycle of stellar birth and death that has been going on since the first stars formed. The rotation of stars is part of this cycle, affecting how they form, how they evolve, and how they die. Galaxies form and evolve in cycles that span cosmic time. Galaxies merge, creating new structures. Gas falls into galaxies, forming new stars. Stars die, returning material to the interstellar medium. This cycle of galactic evolution has been repeating for over 10 billion years, creating the rich diversity of galactic structures we observe. The rotation of galaxies is fundamental to this cycle, maintaining their structure and driving the processes that shape their evolution. These cycles are not separate from rotation, but are manifestations of the same underlying principle. The universe has a rhythm, a pattern of return, a dance that never ends. Rotation creates cycles, cycles create patterns, patterns create structure. The universe's repeating rhythm is written in the turning of planets, the orbit of moons, the spin of stars, the rotation of galaxies, the quantum spin of particles. It is a rhythm that has been going on for nearly 14 billion years and will continue for billions more, a dance that connects the smallest quantum processes to the largest cosmic structures. Why does everything turn? The answer lies in fundamental laws of physics, in the conservation of angular momentum, in the way the universe organized itself from initial chaos into structured systems. But the answer also lies in something deeper. Rotation is not just a consequence of physical laws, but may be a fundamental aspect of how the universe expresses itself, how order emerges from disorder, how complexity arises from simplicity. Tonight, as you drift towards sleep, let the universe's repeating rhythm be your guide. Not the spinning of thoughts or the turning of worries, but the deeper understanding that you are part of a cosmic dance that has been going on for nearly 14 billion years. Every atom in your body, every particle, every force participates in this dance. You are not separate from the universe's rhythm, you are an expression of it. The question of why everything turns connects to the deepest mysteries of physics and cosmology. It touches on the origin of the universe, the formation of structure, the nature of space and time, and the fundamental laws that govern reality. The Big Bang Theory describes how the universe began, but it doesn't fully explain why the universe has the structure it does, why there are galaxies and stars and planets, why there is rotation at every scale. The answer lies in the initial conditions, in the fluctuations that were present from the beginning, in the way those fluctuations grew and created structure through gravitational collapse. The formation of structure in the universe is intimately connected to rotation. As matter clumped together under gravity, any initial rotation was conserved and amplified. This rotation prevented perfect spherical collapse, creating disks and flattened structures. Without rotation, the universe would be very different. Perhaps there would be no spiral galaxies, no planetary systems, no stable orbits. Rotation is not just a property of cosmic structures, but a fundamental aspect of how they form and maintain themselves. The nature of space and time is also connected to rotation. In general relativity, rotating masses drag space-time around with them, creating frame-dragging effects. The rotation of black holes affects their event horizons and the behavior of matter falling into them. The rotation of the universe itself, if it exists, will have profound implications for cosmology. Rotation is not separate from space-time, but is woven into its very fabric. The fundamental laws that govern reality, the conservation of angular momentum, the laws of thermodynamics, the principles of quantum mechanics all relate to rotation in fundamental ways. Angular momentum conservation ensures that rotation persists. The arrow of time connected to entropy increase creates the cycles we observe. Quantum spin, a form of angular momentum, underlies the structure of matter. Rotation is not just a phenomenon, but a fundamental aspect of how the universe works. But the question of why everything turns also connects to something more immediate, more personal, the cycles of your own life, the rhythms of your body, the patterns of your thoughts. Your circadian rhythms are tied to the Earth's rotation. Your life follows patterns that repeat daily routines, weekly cycles, yearly seasons. Your thoughts may cycle, returning to certain themes, certain patterns. These personal cycles are not separate from the cosmic cycles, but are part of the same universal rhythm, the same pattern of return, the same dance that permeates existence at every scale. As you contemplate rotation, remember that you are experiencing it in this very moment. The Earth's rotation creates the day-night cycle that structures your life. The Moon's orbit creates the monthly rhythm of tides and phases. The Earth's orbit creates the yearly cycle of seasons. These are not abstract concepts but lived experiences, patterns that shape your existence in ways both obvious and subtle. The universe's repeating rhythm is a secret that is not hidden, but so present, so constant, that it becomes invisible. Like the air you breathe or the ground beneath your feet, rotation is so fundamental that it fades into the background of awareness. But when you pause to notice it, when you contemplate why everything turns, you touch something essential about the nature of reality itself. Rotation is the universe's way of maintaining order, of preserving structure, of creating patterns that persist across time. It is a form of memory, a way that the universe remembers its initial conditions, carrying forward the angular momentum that was present at the beginning. In this sense, every rotation is a connection to the universe's origin, a link to the moment when structure first began to form. The persistence of rotation across cosmic time is remarkable. The Earth has been rotating for over 4 billion years, and it will continue rotating for billions more. The Sun has been spinning since it formed, and it will continue spinning as it evolves. Galaxies have been rotating for over 10 billion years, maintaining their structure through countless interactions and mergers. This persistence is not accidental, but is guaranteed by the conservation of angular momentum, one of the most fundamental and reliable laws of physics. The stability that rotation provides is crucial for the existence of complex structures. Without rotation, planetary orbits would be unstable, and planets would either fall into their stars or be ejected into space. Without rotation, galaxies would collapse or fly apart. Without the quantum spin of particles, matter itself would not have the structure it does. Rotation creates the stability that allows the universe to have the rich, complex structure we observe. The patterns created by rotation are not just physical but also aesthetic. The spiral arms of galaxies, the rings of Saturn, the bands of Jupiter, the vortices and clouds and oceans, all of these are beautiful patterns created by rotation. The universe's repeating rhythm is not just functional but also beautiful, creating structures that are both necessary for the universe's function and pleasing to observe. This connection between function and beauty, between physics and aesthetics, is one of the deep mysteries of existence. The measurement of rotation across cosmic history reveals the universe's persistent rhythm. Astronomers can measure the rotation of distant galaxies by observing the Doppler shifts of their stars and gas. They can measure the rotation of stars by observing the broadening of spectral lines. They can measure the rotation of planets by tracking surface features. These measurements show that rotation is not just a local phenomenon but a universal one, present at every scale and every epoch. The study of rotation has also revealed the presence of dark matter. The rotation curves of galaxies, showing how orbital speeds vary with distance, cannot be explained by visible matter alone. There must be much more mass, in the form of dark matter, to provide the gravitational pull needed to maintain those rotation speeds. This discovery, made through the study of rotation, has revolutionized our understanding of the universe's composition. The connection between rotation and the formation of structure is profound. Without rotation, the universe would be very different. There might be no spiral galaxies, no planetary systems, no stable orbits. The universe's structure, from the largest scales to the smallest, depends on rotation. The angular momentum present in the early universe has been conserved and has shaped all subsequent structure formation. As you prepare to close your eyes, know that the universe will continue its dance. Planets will keep spinning, stars will keep rotating, galaxies will keep turning. The rhythm will continue as it has for billions of years, as it will for billions more. And you, in your rest, remain part of this eternal dance, connected through rotation to everything that is, everything that was, and everything that will be. The angular momentum that drives this dance was set in motion at the universe's beginning, and it has been conserved ever since, creating a link across cosmic time that connects you to the moment when structure first began to form, when rotation first began, when the universe's repeating rhythm first began to play. The answer to why everything turns lies in one of the most fundamental and beautiful principles in physics, the conservation of angular momentum. This law states that in a closed system, the total angular momentum remains constant unless acted upon by an external torque. It is as fundamental as the conservation of energy or momentum, and it shapes the universe at every scale. Angular momentum is the rotational equivalent of linear momentum. Just as an object in motion tends to stay in motion, an object that is rotating tends to keep rotating. But angular momentum has a special property. It is conserved even more strictly than linear momentum in many situations, because rotational motion can persist even when linear motion is damped by friction or other forces. Consider an ice skater spinning. As they pull their arms in, they spin faster. As they extend their arms, they spin slower. But the total angular momentum, the product of their moment of inertia and angular velocity, remains constant. This is because angular momentum depends on both how mass is distributed moment of inertia and how fast the object is rotating angular velocity. When the distribution changes, the speed adjusts to keep the total constant. This principle is demonstrated in countless ways in everyday life. A figure skater can spin faster by pulling in their arms, a diver can control their rotation rate by changing their body position, a gymnast can flip faster by tucking the body. In all these cases, the conservation of angular momentum is at work, allowing the athlete to control their rotation by changing their moment of inertia. This same principle applies to cosmic scales. When a cloud of gas collapses to form a star, it spins faster as it contracts, just like the ice skater pulling in their arms. The moment of inertia depends on how mass is distributed relative to the rotation axis. For a given mass, the moment of inertia is smaller when the mass is closer to the axis and larger when it's farther away. This is why pulling in your arms makes you spin faster. You're reducing your moment of inertia, so your angular velocity must increase to keep angular momentum constant. This relationship between moment of inertia and angular velocity is fundamental to understanding rotation at all scales. This principle applies to everything in the universe. When a cloud of gas collapses under gravity to form a star, it must spin faster as it contracts, just like the ice skater pulling in their arms. The angular momentum that was present in the original cloud, however small, becomes concentrated as the cloud shrinks, causing it to rotate more rapidly. This is why stars rotate, why planets spin, why galaxies turn. The conservation of angular momentum explains why rotation is so persistent. Once something starts rotating, it tends to keep rotating. There is no natural process that simply stops rotation without transferring that angular momentum to something else. Even when friction slows rotation, the angular momentum is transferred to the surrounding material, not destroyed. It is conserved, preserved, maintained. In the early universe, when matter first began to clump together under gravity, any slight asymmetry, any small amount of rotation in the initial conditions, would be amplified as structures collapsed. A cloud of gas with even a tiny amount of net rotation would spin faster and faster as it contracted, eventually forming a rotating disk. This is how planetary systems form, from rotating protoplanetary disks where planets coalesce from the spinning material. The mathematical beauty of angular momentum conservation is profound. It connects the microscopic to the macroscopic, the quantum to the cosmic. The same principle that explains why an ice skater spins faster when pulling in their arms also explains why galaxies rotate, why planets orbit, why the universe has structure at all. Angular momentum is a vector quantity, meaning it has both magnitude and direction. This directional aspect is crucial. It means that rotation has an axis, a preferred direction in space. This axis can be tilted, can precess, can change orientation, but the total angular momentum vector remains constant. This is why the Earth's rotation axis maintains its tilt relative to the orbital plane, why gyroscopes maintain their orientation, why spinning objects are stable. The conservation of angular momentum also explains why nothing in the universe is perfectly still. Even if you could somehow stop all rotation, any small perturbation, any tiny asymmetry, would create rotation that would then be conserved and amplified. The universe is not static, it is dynamic, and rotation is a fundamental aspect of that dynamism. On cosmic scales, angular momentum shapes the large-scale structure of the universe. Galaxies form with specific rotation patterns because the angular momentum of the original gas clouds is conserved during collapse. The distribution of angular momentum determines whether a galaxy becomes a spiral, an elliptical, or an irregular shape. The rotation curves of galaxies, which show how orbital speeds vary with distance from the center, reveal the presence of dark matter, which provides the gravitational pull needed to maintain those rotation speeds. The conservation of angular momentum is not just a law of physics but a principle that underlies the universe's ability to create and maintain structure. Without it, there would be no stable orbits, no rotating systems, no persistent patterns. Rotation would be temporary, fleeting, impossible to maintain. But because angular momentum is conserved, rotation can persist for billions of years, creating the stable structures we observe in the cosmos. As you contemplate angular momentum, remember that this conservation law is active in your own body right now. The Earth's rotation gives you angular momentum relative to the universe. When you move, you change your moment of inertia, and your body adjusts to conserve angular momentum. Even the spinning of electrons and atoms, the quantum spin of particles, follows principles related to angular momentum conservation, though in the quantum realm the rules are more subtle and strange. The beauty of angular momentum conservation is that it connects the past to the present. The rotation you observe today, whether in a spinning top or a rotating galaxy, carries with it the memory of how that rotation began. The angular momentum was set in motion long ago, and it has been conserved ever since, creating a link across time that connects the universe's origin to its present state. The mathematical formulation of angular momentum conservation is elegant. In classical mechanics, angular momentum L is defined as a cross product of position vector r and linear momentum p, L equals r cross p. For a rotating rigid body, this simplifies to L equals I times omega, where I is the moment of inertia and omega is the angular velocity. The conservation law states that dl/dt equals the net torque, so in the absence of external torques, angular momentum is constant. This mathematical framework applies across all scales. For a planet orbiting a star, angular momentum conservation determines the shape and speed of the orbit. For a spinning neutron star, it determines the rotation rate and how it changes over time. For a collapsing gas cloud, it determines how fast the resulting star or planet will rotate. The same equations, the same principles govern rotation from the quantum scale to the cosmic scale. The conservation of angular momentum also has profound implications for the universe's structure. In the early universe, when structures first began to form, any net angular momentum in a region would be conserved as that region collapsed. This means that the rotation we observe today in galaxies and stars is directly connected to the angular momentum present in the early universe, preserved and amplified through gravitational collapse. The transfer of angular momentum between different components of a system is also crucial. When a protostar forms, it can transfer angular momentum to its protoplanetary disk through magnetic fields and other mechanisms. When galaxies merge, their angular momenta combine in complex ways, creating new rotation patterns. When a binary star system forms, the stars can exchange angular momentum through tidal interactions, affecting their rotation rates and orbital parameters. Why does everything turn? Because angular momentum, once created, must be conserved. Because the universe, in its initial state, had asymmetries and perturbations that created rotation. Because rotation is not just a consequence of physical laws but a fundamental aspect of how the universe organizes itself, how structure emerges from chaos, how order arises from disorder. The conservation of angular momentum is not just a law but a principle that shapes the universe's evolution, creating the rotating structures we observe and maintaining them across billions of years. The birth of rotation in the universe is a story that begins with the Big Bang itself. In those first moments, the universe was extremely hot and dense, filled with energy and particles moving in all directions. But even in this initial chaos, there were tiny fluctuations, small departures from perfect uniformity. These fluctuations would become the seeds of all structure, including rotation. As the universe expanded and cooled, matter began to clump together under gravity. But this clumping was not perfectly symmetric. The initial density fluctuations meant that some regions had slightly more matter than others, and these regions would collapse faster, pulling in surrounding material. But this infall was not perfectly radial. There were always small tangential components, small amounts of motion perpendicular to the radial direction. These tangential motions are the origin of rotation. When material falls into a gravitational potential well, any component of motion that is not directly toward the center creates angular momentum. Even if the initial motion seems random, the process of gravitational collapse naturally creates net rotation. This is because the collapse is not perfectly spherical. There are always asymmetries, always perturbations, always something that breaks perfect symmetry. The mathematics of this process is elegant. As a cloud of gas collapses, its moment of inertia decreases. To conserve angular momentum, its angular velocity must increase. The cloud spins faster and faster as it contracts, eventually flattening into a disk because material along the rotation axis can fall in more easily than material in the equatorial plane, which is supported by centrifugal force. This is how protoplanetary disks form around young stars. The original molecular cloud had some angular momentum, perhaps from turbulent motions, perhaps from interactions with other clouds, perhaps from the large-scale structure of the galaxy itself. As the cloud collapsed to form a star, this angular momentum was conserved, causing the material to spin faster and flatten into a disk. Planets then formed from this rotating disk, inheriting its angular momentum and creating the orbital motion we observe today. The same process occurs on larger scales. When galaxies form, the original gas clouds have angular momentum from their motion in the cosmic web, from interactions with other structures, from the overall expansion and rotation of the universe itself. As these clouds collapse under gravity, the angular momentum is conserved, creating the rotating structures we observe. Spiral galaxies are particularly beautiful examples of this process, their arms tracing out the rotation pattern established billions of years ago. Turbulence plays a crucial role in creating rotation. In a turbulent fluid, there are vortices at all scales, regions where the fluid rotates. These vortices can merge, can interact, can transfer angular momentum between scales. When a turbulent cloud of gas collapses, these vortices become the seeds of rotation. The largest scale vortices determine the overall rotation of the resulting structure, while smaller vortices create local variations in substructure. The origin of rotation is also connected to the universe's initial conditions. The cosmic microwave background shows tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations were present in the very early universe, and they carried with them small velocity perturbations. These velocity fields had vorticity rotational components that would later become the angular momentum of cosmic structures. But where did these initial fluctuations come from? The leading theory is cosmic inflation, a period of extremely rapid expansion in the universe's first fraction of a second. During inflation, quantum fluctuations were stretched to cosmic scales, creating the density and velocity perturbations that would later grow into galaxies and clusters. These quantum fluctuations, when stretched, naturally included rotational components, seeding the universe with the angular momentum that would shape all future structure. The process of rotation's birth is ongoing. Even today, as new stars form in molecular clouds, as new galaxies assemble from cosmic gas, rotation is being created through the same processes: gravitational collapse, turbulence, asymmetry, the conservation of angular momentum. The universe continues to create rotating structures, continuing the pattern that began nearly 14 billion years ago. Why does everything turn? Because the universe began with fluctuations and asymmetries. Because gravitational collapse naturally creates rotation. Because angular momentum, once created, is conserved. Because turbulence and interactions transfer and amplify rotational motion. Because rotation is not an accident, but a natural consequence of how the universe organizes itself from initial chaos into structured systems. The detailed process of how rotation begins in collapsing clouds involves complex physics. As a cloud of gas begins to collapse under gravity, it doesn't do so uniformly. Density fluctuations mean some regions collapse faster than others. Velocity fluctuations mean material has components of motion in all directions, not just radially inward. When material with tangential velocity falls into a gravitational well, it doesn't fall straight in but follows a curved path, creating angular momentum. The Jeans instability, which describes when a cloud of gas becomes unstable to gravitational collapse, doesn't specify how the collapse proceeds. In reality, the collapse is highly non-spherical. Even a small initial asymmetry gets amplified as the cloud contracts. Material falling in from different directions creates a net rotation, and this rotation is then conserved and amplified as the collapse continues. Numerical simulations of star and galaxy formation reveal this process in detail. Starting with nearly uniform conditions but including small random fluctuations, the simulations show that rotation naturally emerges. The final rotation rate depends on the initial conditions, the size of the collapsing region, and the details of the collapse process. But rotation always appears. It's not something that needs to be added, but something that emerges naturally from the physics. The role of magnetic fields in the birth of rotation is also important. Magnetic fields can transfer angular momentum, can create rotational motions through their interactions with charged particles, and can affect how material collapses. In molecular clouds, magnetic fields are often strong enough to significantly influence the collapse process, affecting how rotation develops and how angular momentum is distributed. The interaction between multiple collapsing regions also creates rotation. When two or more density enhancements collapse and interact, their relative motions create angular momentum. Galaxy mergers are dramatic examples of this, where the interaction between two galaxies creates complex rotation patterns, sometimes forming new structures like ring galaxies or creating tidal tails that trace out the rotation. The birth of rotation is not a one-time event, but an ongoing process, a fundamental aspect of how the universe creates structure. Every new star, every new planet, every new galaxy that forms does so with rotation, carrying forward the pattern that began at the universe's origin. Rotation is the universe's way of remembering its initial conditions, of preserving the information encoded in those first fluctuations, of creating order from disorder through the persistent dance of angular momentum. This ongoing creation of rotation ensures that the universe's repeating rhythm continues, that new structures join the cosmic dance, that the pattern of turning persists across cosmic time. Planets and moons dance through space in an intricate choreography of rotation and revolution. This dance is not random but follows precise patterns established billions of years ago, patterns that have been maintained through the conservation of angular momentum and shaped by gravitational interactions. Earth rotates on its axis once every 24 hours, creating the day-night cycle that structures life on our planet. This rotation is not perfectly uniform. It varies slightly due to factors like the distribution of mass within the Earth, the movement of oceans and atmosphere, and the gravitational pull of the Moon and Sun. But these variations are small, and the overall rotation has been remarkably stable over geological time. The Earth's rotation creates several important effects. The Coriolis effect, caused by the rotation, deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. This effect shapes weather patterns, creating the cyclonic and anticyclonic systems we observe. Hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere because of the Coriolis effect. Ocean currents are also deflected, creating the large-scale circulation patterns that transport heat around the globe. Even the paths of long-range missiles must account for the Coriolis effect, which can cause significant deviations over long distances. The rotation also creates a slight bulge at the equator, making the Earth not a perfect sphere but an oblate spheroid, slightly flattened at the poles. This flattening is a result of centrifugal force from the rotation, which pushes material outward at the equator. The Earth's equatorial radius is about 21 kilometers larger than its polar radius, a small but measurable difference. This oblateness affects satellite orbits, which persist due to the Earth's non-spherical shape, and it affects the Earth's gravitational field, which is slightly stronger at the poles than at the equator. The Earth's rotation also affects timekeeping. The length of a day, defined as the time for one rotation, is not perfectly constant but varies slightly due to factors like the movement of mass within the Earth, changes in atmospheric pressure, and interactions with the Moon. These variations are small on the order of milliseconds, but they are measurable and must be accounted for in precise timekeeping systems. The rotation of the Earth is gradually slowing due to tidal interactions with the Moon, making days slightly longer over geological time, though this change is imperceptible on human timescales. The Moon presents a fascinating case of rotation. It rotates on its axis, but it does so in exactly the same time it takes to orbit the Earth, about 27 days. This synchronous rotation, also called tidal locking, means we always see the same face of the Moon from Earth. The far side remained hidden until space probes photographed it in the 1950s. Tidal locking occurs because of gravitational interactions. The Earth's gravity creates a slight bulge on the Moon, and as the Moon rotated, this bulge would lag behind, creating a torque that gradually slowed the Moon's rotation until it matched its orbital period. Once locked, the system is stable, and the Moon will continue to show the same face to Earth for billions of years. Other moons in the solar system are also tidally locked to their parent planets. Jupiter's large moons, Saturn's Titan, and many others all show the same phase to their planets. This is a common outcome of gravitational interactions over long timescales, a natural consequence of how rotation and orbital motion interact. Planetary rotation rates vary dramatically. Jupiter, the largest planet, rotates fastest, completing a turn in less than 10 hours despite its enormous size. This rapid rotation creates strong Coriolis effects, contributing to the planet's distinctive banded appearance in the Great Red Spot, a storm that has persisted for centuries. Venus rotates extremely slowly, taking 243 Earth days to complete one rotation, and it rotates in the opposite direction to most planets' retrograde rotation. This unusual behavior may have been caused by a massive impact early in the solar system's history or by gravitational interactions with the Sun and other planets. The slow rotation means a Venusian day is longer than its year, creating a world with a day-night cycle completely different from Earth's. Mercury is locked in a 3-2-spin orbit resonance with the Sun, rotating 3 times for every 2 orbits. This resonance is stable and prevents the planet from becoming completely tidally locked. The resonance creates a complex day-night pattern, with some regions experiencing extremely long days and nights. The rotation of planets affects their environments in profound ways. Earth's rotation creates the Coriolis effect that shapes global wind patterns and ocean currents. Without rotation, weather would be completely different, with air moving directly from high to low pressure rather than creating the cyclonic and anticyclonic systems we observe. The rotation also creates the alternation of day and night, which drives biological rhythms and affects climate. Planetary rotation also affects the planet's magnetic field. The Earth's magnetic field is generated by the motion of molten iron in the outer core, a process called the dynamo effect. This motion is driven in part by the planet's rotation, which creates the Coriolis forces that organize the convective motions. Without rotation, the Earth might not have a strong magnetic field, which protects the atmosphere from being stripped away by the solar wind. The dance of planets and moons extends to their orbital motions as well. The Earth orbits the Sun in an ellipse, but this ellipse itself rotates slowly, a process called apsidal precession. The Moon's orbit also precesses, with the line of nodes rotating around the Earth. These precessional motions are caused by gravitational perturbations from other bodies and by the non-spherical shape of the Earth. Orbital resonances create stable patterns in the solar system. Jupiter's moons Io, Europa, and Ganymede are locked in a 4-2-1 resonance, meaning Io orbits 4 times for every 2 orbits of Europa and every 1 orbit of Ganymede. This resonance maintains the moon's orbits and prevents them from drifting into unstable configurations. Similar resonances exist throughout the solar system, creating the stable patterns we observe. The formation of planetary systems from rotating protoplanetary disks naturally creates orbital motion. As planets form from the disk material, they inherit the angular momentum of that material, creating the orbital patterns we observe. The spacing of planets, their orbital periods, and their rotations all reflect the angular momentum distribution of the original disk. As you contemplate the dance of planets and moons, remember that you are part of this dance. The Earth's rotation carries you through space, creating the day-night cycle that structures your life. The Moon's orbit creates the monthly rhythm of phases and tides. The Earth's orbit creates the yearly cycle of seasons. These are not abstract astronomical facts but live experiences, patterns that shape existence on Earth. The formation of the solar system itself was a process dominated by rotation. The original solar nebula, a rotating disk of gas and dust, had angular momentum from the molecular cloud from which it formed. As the nebula collapsed, this angular momentum was conserved, causing it to spin faster and flatten into a disk. The Sun formed at the center, while planets formed from the rotating disk material, inheriting its angular momentum. This is why all planets orbit in the same direction and why most rotate in the same direction as well. The spacing of planets follows patterns related to angular momentum distribution. The inner planets are closer together and rotate faster, while the outer planets are farther apart. This pattern reflects how angular momentum was distributed in the original disk and how it was conserved as planets formed. The asteroid belt, located between Mars and Jupiter, may represent material that couldn't form a planet due to Jupiter's gravitational influence, but it still participates in the solar system's rotation. The moons of planets also tell stories of rotation and angular momentum. Many moons are thought to have formed from disks of material around their parent planets, similar to how planets formed around the Sun. These circumplanetary disks had their own angular momentum, creating the orbital patterns we observe. Some moons may have been captured, their orbits and rotation shaped by gravitational interactions over billions of years. The study of exoplanets has revealed the universality of rotation in planetary systems. Planets around other stars also orbit, and many are thought to rotate. The patterns we see in our solar system planets orbiting in roughly the same plane, in the same direction appear to be common, suggesting that the processes that create rotation are universal. The universe's repeating rhythm is written in the motion of planets around stars, a pattern that repeats across the cosmos. The cosmic carousel of planets and moons is a manifestation of the universe's repeating rhythm. These rotations and orbits have persisted for billions of years, maintained by the conservation of angular momentum shaped by gravitational interactions, creating the stable patterns that make life possible. The dance continues, as it has for eons, as it will for eons to come, a testament to the fundamental principles that govern the universe's structure and evolution. Every planet, every moon, every asteroid participates in this dance, carrying forward the angular momentum that was present when the solar system formed, a connection to the universe's origin that persists in every orbit, every rotation, every turn. Stars are born spinning, and this rotation shapes their entire existence. When a cloud of interstellar gas collapses to form a star, it conserves angular momentum, spinning faster as it contracts. The resulting star rotates, and this rotation affects its structure, its magnetic field, its evolution, and its eventual fate. The Sun rotates, but not as a rigid body. Different latitudes rotate at different rates, a phenomenon called differential rotation. At the equator, the Sun completes a rotation in about 25 days, while near the poles it takes over 30 days. This differential rotation is crucial for the Sun's magnetic activity, winding up magnetic field lines and creating the sunspot cycle that repeats approximately every 11 years. The Sun's rotation is slowing down over time due to the solar wind, the stream of charged particles that flows outward from the Sun. This wind carries away angular momentum, gradually reducing the Sun's rotation rate. Early in its life, the Sun may have rotated much faster, completing a turn in just a few days. As it ages, it continues to slow, a process that will continue for billions of years. Young stars typically rotate much faster than older stars. This is because stars lose angular momentum over time through stellar winds and magnetic braking. As a star ages, its rotation slows, and this affects its activity. Fast-rotating stars have stronger magnetic fields and more stellar activity, including flares and coronal mass ejections. Slow-rotating stars are calmer, with weaker magnetic activity. Stellar rotation affects a star's shape. Rapidly rotating stars are not perfect spheres but are flattened at the poles and bulging at the equator due to centrifugal force. This oblateness can be measured through careful observations and provides information about the star's rotation rate and internal structure. The rotation of stars also affects their internal structure and evolution. Rotation creates internal circulation patterns that mix material, bringing fresh hydrogen to the core and extending the star's lifetime. Rotation also affects the strength of convection, which transports energy from the core to the surface. These effects can significantly alter a star's evolution compared to non-rotating models. Magnetic fields in stars are generated by dynamo processes similar to those in planets. The rotation of the star, combined with convection in its interior, creates the motions that generate and maintain magnetic fields. Without rotation, stars would not have strong magnetic fields, and many of the phenomena we observe, from sunspots to stellar flares, would not occur. Pulsars are among the most dramatic examples of stellar rotation. These are neutron stars, the collapsed cores of massive stars that have exploded as supernova. When a star collapses, it conserves angular momentum, so even if the original star rotated slowly, the resulting neutron star can spin hundreds of times per second. The first pulsar discovered, in the Crab Nebula, rotates about 30 times per second, flashing like a cosmic lighthouse as its magnetic poles sweep past our line of sight. Pulsars are incredibly precise clocks, with rotation periods that are stable to better than 1 part in a billion. This precision makes them useful for testing general relativity, detecting gravitational waves, and even for navigation. The gradual slowing of pulsar rotation caused by the emission of radiation can be measured with extraordinary accuracy, providing insights into the physics of these extreme objects. Some pulsars are in binary systems, and the accretion of material from a companion can spin them up to even faster rotation rates. The fastest known pulsars rotate over 700 times per second, approaching the theoretical limit where centrifugal force would tear the star apart. These millisecond pulsars are among the fastest spinning objects in the universe. Stellar rotation also plays a role in stellar death. When a massive star explodes as a supernova, the collapse of the core can create rapid rotation if the original star was spinning. This rotation, combined with the star's magnetic field, can create a magnetar, a neutron star with an extremely strong magnetic field. Magnetars can produce dramatic flares and are among the most magnetic objects known. The rotation of stars affects the formation of planetary systems. A rapidly rotating star might have a stronger stellar wind, affecting a protoplanetary disk. The rotation can also create asymmetries in the disk, influencing where planets form and how they migrate. The final architecture of a planetary system reflects, in part, the rotation of its parent star. As stars age and evolve, their rotation continues to change. Main sequence stars like the Sun gradually slow down. When they become red giants, the outer layers expand, and the rotation slows dramatically due to the increase in moment of inertia. If the star has a binary companion, interactions can transfer angular momentum, creating complex rotation patterns. The study of stellar rotation has revealed much about stellar physics. By measuring rotation rates through spectroscopy, by observing star spots, by studying pulsations, astronomers can probe the internal structure of stars, their ages, their magnetic fields, and their evolution. Rotation is not just a property of stars but a window into their inner workings. The connection between stellar rotation and magnetic activity is profound. The Sun's magnetic field, generated by the dynamo process in its interior, is strongly influenced by rotation. The differential rotation winds up magnetic field lines, creating the sunspot cycle. When sunspots appear, they follow patterns related to the Sun's rotation, appearing first at higher latitudes and then migrating toward the equator as the cycle progresses. This pattern, discovered over a century ago, reveals how rotation and magnetism are intertwined in stellar physics. Stellar rotation also affects the transport of energy within stars. In rotating stars, the Coriolis effect influences convection, creating patterns of circulation that mix material. This mixing can bring fresh hydrogen to the core, extending the star's lifetime. It can also bring heavy elements to the surface, affecting the star's spectrum and evolution. The study of stellar rotation through spectroscopy, by measuring the broadening of spectral lines due to the Doppler effect, provides insights into these internal processes. The evolution of stellar rotation over a star's lifetime follows patterns. Young stars rotate rapidly, often completing a turn in just a few days. As they age, they slow down due to stellar winds and magnetic braking. The rate of spin down depends on the star's mass, with more massive stars having stronger winds and losing angular momentum faster. By measuring rotation rates, astronomers can estimate stellar ages, creating a gyrochronology that complements other age dating methods. Binary star systems add complexity to stellar rotation. When two stars orbit each other closely, tidal interactions can synchronize their rotations with their orbital period, just like the Moon is tidally locked to Earth. This synchronization affects the star's evolution, their magnetic activity, and even their appearance. Some binary systems have stars that are so close they share atmospheres, creating complex rotation patterns as material flows between them. As you contemplate stellar rotation, remember that the Sun's spin affects Earth in subtle ways. The solar wind, shaped by the Sun's rotation and magnetic field, interacts with Earth's magnetosphere, creating auroras and affecting space weather. The Sun's rotation means that different parts of its surface face Earth at different times, creating the solar activity cycle that influences Earth's climate and technology. The rotation of the Sun is not just a property of a distant star but a force that shapes life on Earth. Stars are spinning beacons in the cosmos, their rotation a fundamental aspect of their nature. From the slow rotation of old stars to the rapid spin of pulsars, rotation shapes stellar evolution and creates the phenomena we observe. The universe's repeating rhythm is written in the spin of every star, a pattern that began when the star formed and will continue until the star's final moments, a dance of angular momentum that connects stellar birth to stellar death. Every photon of starlight carries with it information about the star's rotation, encoded in the broadening of spectral lines, and the patterns of variability in the very structure of the light itself. Galaxies are cosmic whirlpools, vast collections of stars, gas, and dark matter rotating around a common center. This rotation is not just a property of galaxies but is fundamental to their structure, their evolution, and their very existence. Understanding galactic rotation has revealed one of the universe's greatest mysteries, dark matter. Spiral galaxies, like the Milky Way, are particularly beautiful examples of cosmic rotation. Their arms trace out the rotation pattern, with material orbiting the galactic center. The rotation is not rigid, like a spinning wheel, but differential, with different parts of the galaxy rotating at different rates. Material closer to the center completes an orbit faster than material farther out, creating the spiral pattern we observe. The rotation curves of galaxies graphs showing how orbital speed varies with distance from the center revealed something unexpected. Based on the visible matter alone, orbital speed should decrease with distance, following Kepler's laws. but observations showed that orbital speeds remain roughly constant out to great distances, far beyond where most of the visible matter is located. This flat rotation curve is one of the strongest pieces of evidence for dark matter. The constant orbital speeds indicate that there is much more mass in galaxies than we can see. This dark matter must be distributed in a halo around the galaxy, providing the gravitational pull needed to maintain those high orbital speeds. Without dark matter, galaxies would not have the rotation curves we observe. They would fly apart or have very different structures. The formation of galactic rotation began in the early universe. As matter clumped together under gravity, the original angular momentum of the gas clouds was conserved, creating rotating structures. The collapse was not perfectly spherical. There were asymmetries and interactions that created net rotation. This rotation, once established, has been maintained for billions of years, shaping the galaxy's evolution. Spiral galaxies maintain their structure through a combination of rotation and density waves. The spiral arms are not fixed structures, but patterns that rotate through the galaxy, like the arms of a pinwheel. Stars and gas move in and out of these arms as they orbit, but the pattern itself persists, creating the beautiful spiral structure we observe. The rotation of galaxies also affects star formation. As gas clouds orbit the galaxy, they can be compressed when they enter spiral arms, triggering the collapse that forms new stars. The rotation creates shear forces that can tear apart gas clouds or bring them together, influencing where and how stars form. The rate of star formation in a galaxy is connected to its rotation, with faster rotating galaxies often having more active star formation. Elliptical galaxies also rotate, but in a more complex way. Unlike spiral galaxies, where most material orbits in a preferred plane, elliptical galaxies have stars moving in all directions. The rotation is more like that of a swarm of bees than a spinning disk. Some elliptical galaxies rotate rapidly, while others have very little net rotation, reflecting different formation histories. At the centers of most galaxies, including the Milky Way, there are supermassive black holes. These black holes can have masses millions or billions of times that of the Sun. The rotation of the galaxy feeds material toward the center, where it can accrete onto the black hole, creating active galactic nuclei and quasars. The black hole itself can rotate, and this rotation affects how it interacts with surrounding material. The rotation of galaxies is not isolated but is part of the larger cosmic web. Galaxies are not randomly distributed but form filaments and sheets, with clusters at the intersections. This large-scale structure has its own patterns of motion, with galaxies moving and rotating within the cosmic web. The rotation of individual galaxies reflects, in part, the angular momentum they acquired from their motion in this larger structure. The study of galactic rotation has advanced through various techniques. Spectroscopy allows astronomers to measure the Doppler shifts of stars and gas, revealing their orbital speeds. Radio observations of neutral hydrogen can map rotation across entire galaxies. Gravitational lensing can probe the mass distribution, including dark matter, that determines the rotation curve. The rotation of the Milky Way itself is something we experience indirectly. The Sun orbits the galactic center at about 220 kilometers per second, taking about 225 million years to complete one orbit a cosmic year. We are part of this rotation, carried along as the galaxy turns. The stars we see in the night sky are also orbiting, creating the patterns that change over millennia as stellar position shift. Galactic rotation connects to the universe's repeating rhythm in profound ways. The rotation that began when galaxies first formed has persisted for billions of years, maintained by the conservation of angular momentum. This rotation shapes galactic structure, drives star formation, and creates the beautiful patterns we observe. The cosmic whirlpools of galaxies are expressions of the same fundamental principles that create rotation at every scale, from quantum spin to planetary rotation to stellar spin. The study of galactic rotation has advanced through multiple observational techniques. Optical spectroscopy measures the Doppler shifts of stars, revealing their orbital speeds. Radio observations of neutral hydrogen can map rotation across entire galaxies, even in regions where stars are sparse. Infrared observations penetrate dust, revealing rotation in obscured regions. Gravitational lensing can probe the mass distribution that determines rotation curves, including the dark matter component. The relationship between galactic rotation and star formation is complex. Spiral arms, which trace the rotation pattern, are sites of active star formation. As gas clouds orbit the galaxy and enter spiral arms, they can be compressed, triggering collapse and starburst. The rotation creates shear forces that can tear apart or bring together gas clouds, influencing where stars form. The rate of star formation in a galaxy is connected to its rotation, with faster rotating galaxies often having more active star formation. Galactic mergers dramatically affect rotation. When two galaxies collide, their angular momenta combine in complex ways. The merger can create new rotation patterns, can transfer angular momentum between components, can create structures like polar ring galaxies where material orbits perpendicular to the main disk. These mergers are not rare events but common occurrences in galactic evolution, showing how rotation adapts and changes as structures interact. The supermassive black holes at galactic centers are also connected to rotation. Material falling toward the black hole has angular momentum, so if it doesn't fall directly in but forms an accretion disk. This disk rotates, and the rotation is crucial for the accretion process, for the generation of jets, for the creation of active galactic nuclei. The rotation of the black hole itself, its spin, affects how it interacts with surrounding material and how it emits radiation. As you contemplate galactic rotation, remember that you are part of this cosmic dance. The Milky Way is rotating, carrying the Sun, the Earth, and you through space. This motion is so vast, so slow, that it is imperceptible on human timescales. But it is real, it is constant, and it connects you to the grandest scales of the universe's structure. The repeating rhythm of galactic rotation is a whisper from the cosmos, a reminder that you are part of something far larger than individual experience, a participant in the universe's eternal dance. The angular momentum that drives this rotation was set in motion billions of years ago when the galaxy first formed, and it has been conserved ever since, creating a link across cosmic time that connects you to the universe's origin. At the smallest scales, rotation takes on a completely different character. Quantum mechanical spin is not rotation in the classical sense. Electrons are not literally spinning like tiny tops, but it shares fundamental properties with angular momentum. This quantum spin is intrinsic to particles, a property they possess that cannot be changed or stopped, and it underlies the structure of matter itself. Quantum spin was discovered through experiments that revealed particles behaving as if they had angular momentum even when they had no spatial extent to rotate. Electrons, protons, neutrons, and other fundamental particles all have spin, measured in units of Planck's constant. This spin is quantized, meaning it can only take on specific discrete values, not any arbitrary amount. Electrons have spin 1/2, meaning their spin angular momentum is half of Planck's constant divided by 2 pi. This half-integer spin makes electrons fermions, particles that obey the Pauli exclusion principle. This principle states that no two fermions can occupy the same quantum state, which is why electrons in atoms occupy different energy levels and orbitals, creating the structure of matter. The spin of electrons is crucial for atomic structure. In an atom, electrons occupy orbitals that have specific shapes and orientations determined by quantum mechanics. The spin of each electron, combined with its orbital angular momentum, determines the atom's magnetic properties and how it interacts with light and other atoms. Without quantum spin, atoms would be completely different, and chemistry as we know it would not exist. The spin of particles also creates magnetic moments. A spinning charged particle creates a magnetic field, just like a classical rotating charge. This is why electrons and other charged particles with spin behave like tiny magnets. The interaction between these magnetic moments and external magnetic fields is the basis for many technologies, from MRI machines to computer hard drives. Fermions, particles with half-integer spin like electrons, make up matter. Bosons, particles with integer spin like photons, carry forces. This fundamental distinction shapes the universe. Fermions cannot occupy the same state, creating the structure and diversity of matter, while bosons can occupy the same state, allowing them to create coherent phenomena like laser light. The spin of particles is also connected to the direction of time. In quantum field theory, particles and antiparticles are related by time reversal, and their spins are connected to this relationship. The spin statistics theorem, one of the most fundamental results in quantum mechanics, connects the spin of particles to their quantum statistics, determining whether they are fermions or bosons. Quantum spin is not just a property of individual particles but can be entangled between particles. Two electrons can be in an entangled state where their spins are correlated, even when separated by large distances. Measuring the spin of one instantly determines the spin of the other, a phenomenon that science then called spooky action at a distance, but which has been verified in countless experiments. The spin of atomic nuclei also plays important roles. Many nuclei have non-zero spin, creating nuclear magnetic moments. These moments interact with external magnetic fields, a phenomenon used in nuclear magnetic resonance and MRI. The precise frequencies at which nuclei resonate depend on their spin and the local magnetic environment, allowing detailed imaging of the human body and other materials. In condensed matter physics, the collective behavior of spins creates fascinating phenomena. Ferromagnetism arises when the spins of many electrons align, creating a permanent magnetic field. Antiferromagnetism occurs when spins alternate, cancelling out the overall magnetization. These magnetic phases and transitions between them are areas of active research, with applications in technology and fundamental physics. The quantum Hall effect, discovered in two-dimensional electron systems, is intimately connected to spin. In strong magnetic fields, the quantum mechanical behavior of electrons creates quantized resistance values that depend on fundamental constants. The fractional quantum Hall effect, where the resistance takes fractional values, reveals the collective behavior of electrons and may be related to exotic quasi-particles with fractional spin. Spin also plays a role in quantum computing. Quantum bits, or qubits, can be encoded in the spin states of particles like electrons or atomic nuclei. The ability to manipulate and measure these spins is crucial for building quantum computers, which could solve certain problems far faster than classical computers. The connection between quantum spin and classical rotation is subtle but profound. While spin is not literal rotation, it behaves mathematically like angular momentum. It is conserved, it can be transferred between particles, and it creates magnetic effects similar to those of rotating charges. This connection suggests that spin and rotation, though different in nature, are related aspects of how the universe expresses angular momentum at different scales. The discovery of quantum spin was one of the great surprises of early quantum mechanics. When electrons were found to behave as if they had angular momentum, even though they were point particles with no spatial extent to rotate, physicists had to develop new concepts. The spin of electrons was discovered through the CERN-Gerlach experiment, where a beam of silver atoms was split by a magnetic field, revealing that electrons have two possible spin states, up or down. The mathematical description of spin uses the same framework as angular momentum but with crucial differences. Spin operators satisfy commutation relations similar to those of orbital angular momentum, but spin can take half-integer values, which orbital angular momentum cannot. This half-integer property is what makes electrons fermions and leads to the Pauli exclusion principle, which is fundamental to the structure of matter. The connection between spin and statistics, encoded in the spin statistics theorem, is one of the most profound results in quantum field theory. It states that particles with half-integer spin must be fermions, obeying the Pauli exclusion principle, while particles with integer spin must be bosons, which can occupy the same quantum state. This theorem connects the spin of particles to their quantum behavior in ways that are not obvious but are absolutely fundamental. Spin-orbit coupling is another crucial quantum phenomenon. In atoms, the spin of an electron interacts with its orbital angular momentum, creating fine structure in atomic spectra. This coupling affects the energy levels of atoms, the chemical properties of elements, and the behavior of materials. In solids, spin-orbit coupling can create topological phases of matter with properties that are protected by symmetry and topology. The study of spin in condensed matter has revealed fascinating phenomena. Spintronics, the field that exploits electron spin for technology, has created devices like spin valves and magnetic tunnel junctions that are used in computer hard drives and memory. The manipulation of spin, rather than just charge, opens new possibilities for electronics and computing. As you contemplate quantum spin, remember that every atom in your body contains particles with spin. The electrons spinning around atomic nuclei, the nuclei themselves with their own spins, all contribute to the structure and properties of matter. The magnetic field of your body, though weak, arises from these quantum spins. The very existence of solid matter, the fact that you don't fall through the floor, depends on the Pauli exclusion principle, which in turn depends on quantum spin. Without quantum spin, matter as we know it would not exist. Quantum spin is the smallest term, the most fundamental expression of the universe's repeating rhythm at the microscopic scale. It underlies the structure of matter, creates magnetic phenomena, and connects to the deepest aspects of quantum mechanics. The spin of particles is not just a curiosity but a fundamental property that shapes reality at the most basic level, a whisper of rotation that echoes from the quantum realm to the cosmic scale. Every rotation you observe, from a spinning top to a rotating galaxy, ultimately traces back to the quantum spin of particles, connecting the macroscopic dance of the universe to the microscopic dance of quantum mechanics. The universe is filled with cycles and rhythms that repeat on timescales from fractions of a second to billions of years. These cycles are not separate from rotation but are manifestations of the same underlying principle. The universe is patterns that recur, rhythms that echo, a dance that repeats. Understanding these cycles reveals the deep connection between rotation and the flow of time itself. The most immediate cycle is the day-night rhythm created by Earth's rotation. Every 24 hours, the planet completes one turn, bringing each location through periods of light and darkness. This cycle structures life on Earth, driving circadian rhythms in plants and animals, including humans. The rotation of the Earth is so constant, so reliable, that it has been used as a basis for timekeeping for millennia. But the day-night cycle is not perfectly uniform. The Earth's rotation is gradually slowing due to tidal interactions with the Moon. Over millions of years, days are getting longer, though the change is so slow that it's imperceptible on human timescales. The Moon's gravity creates tides in the Earth's oceans and solid body, and the friction from these tides gradually transfers angular momentum from the Earth's rotation to the Moon's orbit, causing the Earth to slow and the Moon to move farther away. The monthly cycle of the Moon's phases is another fundamental rhythm. As the Moon orbits the Earth, different portions of its sunlit side face Earth, creating the cycle from new moon to full moon and back. This cycle has been used for timekeeping, for agriculture, for cultural and religious practices. The gravitational effects of this cycle create the tides, which themselves follow a monthly rhythm as the moon's position relative to the sun changes. The yearly cycle of seasons is created by Earth's orbit around the sun combined with the tilt of Earth's rotation axis. As the Earth orbits, different hemispheres receive more or less direct sunlight, creating the seasonal variations. This cycle structures agriculture, migration patterns, and many aspects of life on Earth. The orbit itself takes about 365.25 days, requiring the leap year system to keep calendars aligned with the seasons. Life itself is filled with cycles. Organisms have circadian rhythms, daily cycles of activity and rest. Many plants and animals have seasonal cycles, breeding and migrating in response to changing conditions. Life cycles, from birth to death, are themselves cycles, with patterns that repeat across generations. The very process of evolution can be seen as a cycle of variation, selection, and reproduction, creating patterns that recur and evolve over time. On longer timescales, there are geological cycles. The rock cycle transforms igneous rock to sedimentary to metamorphic and back. The water cycle moves water through evaporation, condensation, and precipitation. The carbon cycle moves carbon through the atmosphere, oceans, and biosphere. These cycles are driven by various forces, including rotation, but they create repeating patterns that structure Earth systems. Stellar evolution follows cycles as well. Stars are born from collapsing gas clouds, burn hydrogen in their cores, evolve through various stages, and eventually die, returning material to the interstellar medium where new stars can form. This stellar life cycle has been repeating for billions of years, creating the elements that make up planets and life. The rotation of stars is part of this cycle, affecting how stars evolve and how they end their lives. Galactic evolution also has cyclical aspects. Galaxies form, evolve, merge with other galaxies, and can be reborn through new star formation. The rotation of galaxies is maintained through these processes, with angular momentum being conserved even as galaxies interact and merge. The spiral arms of galaxies are patterns that persist even as individual stars move through them, creating a cycle of structure that maintains itself. The universe itself may have cycles. Some theories propose that the universe undergoes cycles of expansion and contraction, a Big Bang followed by a Big Crunch, followed by another Big Bang. While current observations suggest the universe will expand forever, the possibility of cosmic cycles remains an area of theoretical investigation. Even if the universe doesn't cycle in this way, the patterns within it, the formation and evolution of structure, the cycles of stellar and galactic evolution create rhythms that repeat on cosmic timescales. The arrow of time, the fact that time seems to flow in one direction, is connected to these cycles. While individual processes may be reversible at the microscopic level, the overall flow of time creates an arrow. But within this arrow, there are cycles, patterns that repeat. The universe is not simply moving toward greater disorder, it is creating and maintaining patterns, cycles that persist even as entropy increases. The relationship between cycles and rotation is profound. Many cycles are directly caused by rotation, day and night, the phases of the moon, the seasons. Others are maintained by rotation, the structure of galaxies, the patterns of weather, the flow of ocean currents. Rotation creates stability, allowing cycles to persist over long timescales. Without rotation, many of these cycles would not exist or would be fundamentally different. The study of cycles reveals the universe's capacity for pattern and rhythm. From the quantum oscillations of particles to the orbital motions of planets to the rotation of galaxies, the universe is filled with repeating patterns. These patterns are not static but dynamic, maintained by the conservation of angular momentum and other fundamental principles, creating the rich tapestry of structure and process that we observe. As you contemplate cycles and rhythms, remember that you are part of many of them. Your body has circadian rhythms tied to the day-night cycle. Your life follows patterns that repeat across days, weeks, years. You are part of the cycle of life, connected to generations before and after. You are part of the cosmic cycles, the rotation of the Earth, the orbit around the Sun, the motion through the galaxy. The relationship between cycles and entropy, the measure of disorder, is profound. While entropy generally increases, creating the arrow of time, cycles represent local decreases in entropy, islands of order in a universe tending toward disorder. A plant growing, a star forming, a galaxy rotating, these are all processes that create order, that decrease entropy locally, even as the universe's total entropy increases. Cycles are the universe's way of creating and maintaining structure despite the overall trend toward disorder. Biological cycles are particularly rich examples of how rotation and cycles structure life. Circadian rhythms, the daily cycles of activity and rest, are found in almost all living things. These rhythms are not just responses to the day-night cycle, but are generated internally by biological clocks that can persist even in constant conditions. The rotation of the Earth created the environmental cycle that shaped the evolution of these internal clocks, but the clocks themselves have become independent, creating rhythms that structure life from the cellular to the organismal level. Seasonal cycles drive migration, hibernation, breeding, and many other biological processes. Animals and plants have evolved to synchronize their life cycles with the seasonal changes created by Earth's orbital motion and axial tilt. These cycles create patterns that repeat year after year, yet each cycle is unique, creating the variation that drives evolution. The repeating rhythm of seasons is not just a physical phenomenon, but a biological force that shapes ecosystems and evolution. The water cycle, driven by solar energy and Earth's rotation, is a fundamental cycle that structures Earth's systems. Water evaporates from oceans, forms clouds, falls as precipitation, flows in rivers, and returns to oceans. This cycle transports energy, shapes landscapes, and makes life possible. The rotation of the Earth creates the Coriolis effect that influences weather patterns, which in turn drive the water cycle, showing how rotation creates cycles that structure planetary systems. Geological cycles operate on much longer timescales. The rock cycle transforms rock from one type to another over millions of years. The carbon cycle moves carbon through the atmosphere, oceans, and lithosphere over similar timescales. The plate tectonic cycle, driven by Earth's internal heat and rotation, creates and destroys crust, shapes continents, and drives mountain building. These cycles are not perfectly repeating but have patterns that recur, creating the geological history of Earth. The universe's repeating rhythm is not just a physical phenomenon, but a pattern that structures existence at every scale. From the spin of electrons to the rotation of galaxies, from daily cycles to cosmic evolution, the universe dances to rhythms that echo through space and time. These cycles are the universe's way of creating order, of maintaining structure, of expressing the fundamental principles that govern reality. In contemplating these cycles, you touch something essential about the nature of existence itself, that the universe is not random but patterned, not chaotic but rhythmic, not static but dynamically repeating, a dance that has been going on for billions of years and will continue for billions more. Every cycle, from the quantum oscillations of particles to the orbital motions of planets to the rotation of galaxies, is part of this grand pattern, a manifestation of the universe's repeating rhythm that structures reality at every scale. The physics of rotation encompasses a rich set of phenomena that arise from the fundamental principles of angular momentum, forces, and the structure of space-time itself. Understanding these phenomena reveals why rotation is so pervasive and how it shapes the universe at every scale. Centrifugal force is perhaps the most familiar rotational effect. When an object moves in a circle, it experiences an outward force that seems to push it away from the center. This is not a real force, but a fictitious force that arises in rotating reference frames. From an inertial frame, the object is simply trying to move in a straight line, but the circular path constrains it, requiring a centripetal force to keep it on that path. Centripetal force is the real force that keeps objects moving in circular paths. For a planet orbiting a star, gravity provides the centripetal force. For a car turning a corner, friction between the tires and road provides the centripetal force. The relationship between centripetal force, mass, velocity, and radius determines the motion, creating the stable orbits and rotations we observe. The Coriolis effect is another crucial rotational phenomenon. In a rotating reference frame, moving objects appear to be deflected. In the northern hemisphere, objects are deflected to the right, in the southern hemisphere to the left. This effect shapes weather patterns, creating the rotation of storms and the patterns of global wind circulation. Without the Coriolis effect, weather would be completely different, with air moving directly from high to low pressure rather than creating the cyclonic systems we observe. The Coriolis effect also affects ocean currents, creating the large-scale circulation patterns that transport heat around the globe. It affects the paths of long-range projectiles, requiring corrections for artillery and missiles. It even affects the flow of water down drains, though the effect is too small to be noticeable in most everyday situations. Precession is the slow change in the orientation of a rotating object's axis. The Earth's rotation axis precesses, completing a full cycle about every 26,000 years. This precession is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge, creating a torque that causes the axis to trace out a cone in space. This precession affects which stars are visible as a pole star and contributes to long-term climate variations. Nutation is a smaller, faster wobble superimposed on precession. For the Earth, nutation has a period of about 18.6 years and is caused by variations in the Moon's orbit. These small oscillations add complexity to the Earth's rotational motion, though they are much smaller than the main precession. Gyroscopes exploit the physics of rotation to maintain orientation. A spinning gyroscope resists changes to its axis of rotation, a property called gyroscopic stability. This stability arises from the conservation of angular momentum and the way forces act on rotating objects. Gyroscopes are used in navigation, in spacecraft attitude control, and in many other applications where maintaining orientation is crucial. Frame dragging is a remarkable effect predicted by general relativity. A massive rotating object drags spacetime around with it like a spinning ball in a viscous fluid. This effect has been measured around Earth using precise satellite experiments, confirming one of general relativity's predictions. Around rotating black holes, frame dragging can be extreme, creating regions called ergospheres where it's impossible to remain stationary. The lens-lowering effect, another general relativistic phenomenon, causes the orbits of objects around a rotating mass to precess. This effect is small but has been measured, providing another test of general relativity and revealing how rotation affects the structure of space-time itself. Rotation also plays a role in fundamental forces. The weak nuclear force, which is responsible for certain types of radioactive decay, violates parity symmetry, meaning it distinguishes between left and right. This violation is connected to the spin of particles and reveals a fundamental asymmetry in the laws of physics. The universe is not perfectly symmetric, it has a preferred handedness that is connected to rotation and spin. The mathematics of rotation is elegant and powerful. Rotations in three-dimensional space can be described using rotation matrices or quaternions, mathematical objects that capture the full complexity of rotational motion. These mathematical tools are essential for computer graphics, robotics, spacecraft navigation, and many other applications. The relationship between rotation and energy is also important. Rotating objects have kinetic energy proportional to their moment of inertia in the square of their angular velocity. This rotational energy can be stored, transferred, and converted to other forms. Flywheels use this principle to store energy, spinning up to high speeds and then releasing that energy when needed. Tidal forces, created by differences in gravitational pull across an object, are connected to rotation. The moon's gravity creates tides on Earth, and the friction from these tides transfers angular momentum, affecting both Earth's rotation and the moon's orbit. Similar processes occur throughout the universe, where gravitational interactions and rotation are intimately connected. The physics of rotation reveals why rotation is so persistent and pervasive. Once angular momentum is created, it is conserved. Forces can change how that momentum is distributed, but they cannot simply make it disappear. This conservation, combined with the natural processes that create rotation, gravitational collapse, turbulence, interactions, ensures that rotation is a fundamental aspect of the universe's structure. As you contemplate the physics of rotation, remember that these principles are active in your own experience. When you turn a corner, centripetal and centrifugal forces are at work. The Coriolis effect, though too small to notice directly, shapes the weather you experience. The Earth's precession, though slow, affects the night sky over millennia. The physics of rotation is not abstract but immediate, shaping the world around you in ways both obvious and subtle. The relationship between rotation and energy is fundamental. Rotating objects have kinetic energy, and this energy can be significant. A spinning neutron star contains enormous rotational energy, which it gradually loses through radiation, slowing its rotation. The energy stored in Earth's rotation, though vast, is gradually being transferred to the moon's orbit through tidal interactions. This transfer of energy and angular momentum is a slow but inexorable process that shapes the evolution of the Earth-Moon system. Rotational energy can also be converted to other forms. When a protostar collapses, rotational energy can be converted to heat through friction and turbulence. When galaxies merge, rotational energy is converted to random motion, heating the gas and affecting star formation. These conversions show how rotation is not isolated, but connected to other forms of energy participating in the universe's energy budget. The stability of rotating systems is a crucial aspect of their physics. A spinning top is stable because of gyroscopic effects, resisting changes to its orientation. A planet's orbit is stable because of the balance between gravitational force and the centripetal force needed for circular motion. A galaxy's rotation is stable because of the balance between gravity and the centrifugal force from rotation. This stability allows rotating systems to persist for billions of years, creating the long-lived structures we observe. The mathematics of rotation in 3 dimensions is rich and complex. Rotations can be described using rotation matrices, which are orthogonal matrices with determinant 1. They form a group called SR3, the special orthogonal group in 3 dimensions. This group structure underlies many aspects of rotational physics, from the behavior of gyroscopes to the quantum mechanics of angular momentum. Quaternions provide another mathematical framework for describing rotations. Unlike rotation matrices, quaternions avoid problems with gimbal lock and provide efficient ways to interpolate between rotations. They are widely used in computer graphics, robotics, and spacecraft navigation, showing how the mathematics of rotation has practical applications. The connection between rotation and symmetry is profound. Rotational symmetry means that a system looks the same when rotated by certain angles. This symmetry leads to conservation laws through Noether's theorem, which states that every continuous symmetry corresponds to a conserved quantity. Rotational symmetry corresponds to the conservation of angular momentum, showing how symmetry and conservation are deeply connected. The mathematics and physics of rotation connect the smallest quantum spins to the largest cosmic rotations, revealing a unified framework that describes how the universe turns. This framework is not just descriptive but predictive, allowing us to understand and anticipate rotational phenomena across all scales. In this understanding, we glimpse the deep structure of reality, principles that govern how the universe expresses itself through the eternal dance of rotation. The same mathematical tools, the same physical principles, apply from the quantum realm to the cosmic scale, showing that rotation is not just a phenomenon but a fundamental aspect of how the universe is structured, how it evolves, how it expresses itself through the eternal turning that permeates existence. The journey to rotation's mysteries has revealed a universe that turns at every scale, from quantum spin to galactic rotation, from daily cycles to cosmic evolution. This turning is not random but follows fundamental principles: the conservation of angular momentum, the effects of forces, the structure of spacetime itself. Rotation is the universe's repeating rhythm, a pattern that has persisted for billions of years and will continue for billions more. As you prepare to close your eyes, remember that you are part of this eternal dance. The Earth rotates beneath you, carrying you through space. The Moon orbits, creating monthly rhythms. The Earth orbits the Sun, creating yearly cycles. The Sun orbits the galactic center, on a journey that takes hundreds of millions of years. And on smaller scales, the particles that make up your body have quantum spin, a fundamental property that cannot be stopped. Why does everything turn? The answer lies in the fundamental laws of physics, in the conservation of angular momentum, in the way the universe organized itself from initial chaos into structured systems. But the answer also lies in something deeper. Rotation is not just a consequence of physical laws, but maybe a fundamental aspect of how the universe expresses itself, how order emerges from disorder, how complexity arises from simplicity. The universe's repeating rhythm is a secret that is not hidden, but so present, so constant, that it becomes invisible. Like the air you breathe or the ground beneath your feet, rotation is so fundamental that it fades into the background of awareness. But when you pause to notice it, when you contemplate why everything turns, you touch something essential about the nature of reality itself. Rotation creates stability. It allows systems to persist, to maintain their structure over long timescales. Planets orbit in stable configurations because of angular momentum conservation. Galaxies maintain their shape because of rotation. Even the quantum spin of particles creates the stability that allows matter to exist. Without rotation, the universe would be fundamentally different, perhaps impossible. The cycles you experience day and night, the phases of the moon, the seasons are all manifestations of rotation. These cycles structure your life, create rhythms that organize experience, provide patterns that recur in comfort. The universe's repeating rhythm is not just a physical phenomenon, but a pattern that shapes existence, that creates the temporal structure within which life unfolds. As consciousness fades and sleep approaches, let the universe's repeating rhythm be your guide. Not the spinning of thoughts or the turning of worries, but the deeper understanding that you are part of a cosmic dance that has been going on for nearly 14 billion years. Every atom in your body, every particle, every force participates in this dance. You are not separate from the universe's rhythm, you are an expression of it. The Earth will continue its rotation, bringing you through another day-night cycle. The Moon will continue its orbit, creating another monthly rhythm. The seasons will continue their cycle, the years will pass, and the cosmic dance will go on. This continuity, this persistence, is not just a physical fact, but a source of comfort, a reminder that you are part of something vast and enduring. Why does everything turn? Because angular momentum, once created, is conserved. Because the universe, in its initial state, had asymmetries that created rotation. Because rotation is not just a consequence of physical laws, but a fundamental aspect of how the universe organizes itself. Because turning is the universe's way of maintaining order, of creating patterns, of expressing the deep structure of reality. The universe's repeating rhythm is the answer to why everything turns. It is not a single cause, but a pattern that emerges from fundamental principles, a dance that has been going on since the universe began and will continue until the universe ends, or perhaps beyond. In this rhythm, in this turning, the universe expresses something essential about itself, that it is dynamic, not static, patterned, not random, rhythmic, not chaotic. Rest now with the understanding that you are part of this eternal dance. The rotation will continue, the cycles will repeat, the rhythm will persist. You are connected through rotation to everything that is, everything that was, and everything that will be. The universe's repeating rhythm is your rhythm, the turning of the cosmos is your turning, the eternal dance is your dance. Sleep well with the universe's repeating rhythm as your companion. Let the turning of the Earth, the orbit of the Moon, the dance of the planets, the spin of the stars, the rotation of the galaxies lull you toward rest. You are a part of this dance, always have been, always will be. The rhythm continues as it has for billions of years, as it will for billions more. Rest in this knowledge, find peace in this continuity, sleep with the understanding that you are held in the universe's eternal, repeating, turning dance. The journey through rotation's mysteries has revealed a universe that turns at every scale, from quantum spin to galactic rotation, from daily cycles to cosmic evolution. This turning is not random, but follows fundamental principles: the conservation of angular momentum, the effects of forces, the structure of space-time itself. Rotation is the universe's repeating rhythm, a pattern that has persisted for billions of years and will continue for billions more. The question, why does everything turn, has many answers. each revealing a different aspect of the universe's structure. It turns because angular momentum is conserved, because the universe began with asymmetries, because gravitational collapse creates rotation, because turbulence and interactions amplify it, because rotation creates stability, because it's a fundamental aspect of how the universe organizes itself. But perhaps the deepest answer is that turning is simply what the universe does, a fundamental expression of its nature, a pattern that emerges from the most basic principles of physics. As you prepare to close your eyes, remember that you are part of this eternal dance. The Earth rotates beneath you, the Moon orbits above, the Sun spins in space, the galaxy turns around its center. Every atom in your body contains particles with quantum spin. Every cell in your body has rhythms tied to the Earth's rotation. Every breath you take is part of cycles that have been going on for billions of years. The universe's repeating rhythm is not just a physical fact but a source of comfort, a reminder of continuity, a connection to something vast and enduring. The rotation will continue, the cycles will repeat, the dance will go on. You are a part of this dance, always have been, always will be. The angular momentum that drives the universe's turning was set in motion at the beginning, and it has been conserved ever since, creating a link across time that connects you to the universe's origin. Rest now, with the understanding that you are held in this rhythm, that you are part of this dance, that the turning of the cosmos is your turning too. Let the knowledge that everything turns, that this turning is fundamental and eternal, bring you peace. The universe's repeating rhythm is your rhythm, the eternal dance is your dance, the turning is your turning. Sleep well with the universe's repeating rhythm as your companion. Let the gentle rotation of the Earth, the steady orbit of the Moon, the patient turn of the galaxy lull you toward rest. You are part of something vast and beautiful, connected through rotation to everything that is, everything that was, and everything that will be. The rhythm continues, as it has for billions of years, as it will for billions more. Good night. Rest with the universe's repeating rhythm. Fall asleep knowing why everything turns, knowing that you are part of this eternal dance, knowing that the universe's repeating rhythm is your rhythm too. The turning continues, the dance goes on, and you, in your rest, remain part of it all, connected through the fundamental principle that makes everything turn, the conservation of angular momentum, the persistence of rotation, the eternal rhythm of the universe itself.